Well, hello there. We're back here today with compounds and reactions. Today, we wanted to be talking off about compounds. Most everything is a compound, whether it's the table salt, whether it's the pencil that you're working with, the book, your computer. Every part of that is basically a compound. Very few things are pure substances. So, some elements combine to form compounds that share characteristics. Some elements combine to form characteristics unlike any of the elements that make it. An example, salt. It's sodium and chlorine. The sodium is soft, gray, and it's a shiny metal. Chlorine is yellow, deadly gas. Now, some people might say, well, salt is deadly, Mr. Kimmel, so it shares that characteristic. That's not exactly what we're talking about here. Salt is not soft. It's not gray. It's not, sometimes it is shiny, but it's not yellow. It's not a deadly gas. What does not form any compounds? Well, the answer to that is the noble gases. The noble gases, for the most part, do not combine to form any compounds. And what we're talking about now is the noble gases are the elements that on our periodic table are going to be clear over. This is our periodic table here, and I'm making a real quick and sloppy one. The periodic table, this column over here, this one over here is the noble gases. All right, they're going to have, and the reason they don't combine for the most part is, if you remember, that column right there says that its last energy level is full, which means that it's not very reactive. It doesn't want to combine with any other element because its last energy shell or level is already full. Isotopes, as we discussed, we'll be talking about isotopes tonight. Isotopes have the same number of protons. So we can have, for example, we can have a carbon 15, we can have a carbon 12, we can have a carbon 11. That last number is making reference to the mass number, so it's telling us what type of isotope it is. But what I want you to understand is all carbon is going to have 6 protons, so they will have the same number of protons. Many have a different number of neutrons, and that's why we had the carbon 11, carbon 12, carbon 13, carbon 14. It's just a specific way to talk about what type of carbon atom do we have. And if it has the same number of protons, then the only thing that can be different is the number of neutrons that it has. An example of this. 15 is the isotope number and the mass number. Well, how do we find the number of neutrons? It would be 15 minus 6. The mass number is the protons and neutrons. So if we take 15 and subtract from it the number of protons, that's going to tell us that we have 10 neutrons left. Not 9 neutrons, not 10. 9 newtons. Not 9 newtons, 9 neutrons, I'll get it right. Find the number of protons in the element. Well, that's what we're doing here. We find the number of protons, we subtract it, and that tells us the number of neutrons then. So, an isotope, there's many elements can have many different isotopes. They're the same element because they have the same number of protons. They have the same number of protons, but they are called different because they have a different number of neutrons. Alright, carbon 12. Question, how many neutrons, how many protons? Well, it's carbon, and as we've learned before, carbon has an atomic number of 6. So in this case, it's going to have 6 protons. Well, 6 plus what gives me 12? Well, it has to have, carbon 12 has to have 6 neutrons. Carbon 14, how many does it have? It's got 6 protons. Plus what gives me 14? It has to be 8. The last example, carbon 20, 6 protons plus 14 neutrons gives me 20 for total. Mass number. Well, we've kind of already talked about this mass number here a little bit. All right. In our periodic table, it gives us these symbols here. in this bottom number here isn't exactly the mass number. It gives us the atomic mass number. And what the atomic mass number is it is an average of the sample of atomic mass. Actually, I may have said that just the opposite. This is the mass number. The atomic mass number is this one that's specific to that example. So how do we find out the mass number? Well, it's just some simple math. Let's say in a sample of carbon, there was 5 carbon 12s and there were 10 carbon 14s. Well, 5 carbon 12s means there's 60 total mass units. There was 30 protons and 30 neutrons for a total of 60. And in that sample, we also had 10 carbon 14s. Well, that means there was 60 protons and 80 neutrons in that example. If we take these two and add them up, we get a total of 200. There was a total of 15 different atoms, so we take our total mass units and divide it by the total number of atoms we had, and we find out on average that it would be 13.3333. Well, on a periodic table, the number they give us down here at the bottom is they've taken a lot of samples, and they've calculated out what the average is. Now this could be a specific average I had for this specific sample of 15. This over here, this is the specific number for all of the different isotopes. Right? If you do this exact same math for all of the isotopes, nitrogen is going to have a number of 14.01 is what its mass number is. Formula, chemical shorthand way for naming a compound. Some examples, NaCl, well, that's salt. Right, hopefully you guys have learned that over the years. H2O, that's water. Hopefully that's pretty simple for you. Well, the subscript tells us how many atoms of a specific element there are in a compound. So, and I want you to know that no number means there is one atom. So in H2O, the ratio is 2 hydrogen to 1 oxygen, or 2 to 1. Fe2O3, the ratio is 2 iron, 3 oxygen, or 2 to 3. Chemical changes. Alright, chemical changes caused from the gaining or losing of electrons. A chemical bond is a force that holds together atoms in a compound. So let's talk about some of these chemical changes from the gaining or losing of electrons. All atoms want to become stable. How do they become stable? Well, that means that last energy level, however many energy levels they have, that last one, an atom is stable when its last energy level is full of electrons. We typically show this with a dot diagram. This is a model where we only show the number of electrons in an element in the last energy level. So for example, carbon. Carbon has 6 protons and 6 electrons. 2 of them are in the first level. So how many electrons are in the last one? There would be 4. So in a dot diagram, we'd put 4 electrons out here. Notice that it's not full because carbon wants its last energy level to be full, so we could have 4 total more for it to have 8 in its last energy level. Typically, we write down the chemical symbol, and then we use its 4 sides. We have top, I put 2 on top. You could put 2 on bottom. You could put 2 on right. You could put 2 on left. It's just kind of arbitrary where you choose to put them. Well, an element has 1 electron in its outer shell. Would look like this. If I go over here to sodium, sodium is in the first column. So that means its electrons are only in, that means it has 1 electron in its outermost shell. So I would put 1 dot above sodium. Chlorine, as you can see, it's missing 1 electron. It has 7 electrons in its outermost shell. Well, what you can see then is a lot of times sodium and chlorine will combine, and what that'll do now is that will allow chlorine to have 8 electrons in its outermost shell and sodium to have 8 electrons in its outermost shell. They will, in essence, share I'm sorry, they don't share. I want to take that off there. They won't share. That couldn't be more wrong by saying that. Got ahead of myself there. Sodium's going to lose its electron. Chlorine's going to gain it. So sodium's going to have a positive charge. Chlorine's going to have a little bit, one extra electron, so it'll have a negative charge. And now we can tell by electric charges that they're going to be attracted to each other, and that's why we have that. That's why that happens. Well, hey, I hope this has been beneficial for you. I'll see you on the flip side.